Yes, Afrin, you can start.
Okay.
Afrin, 1 minute. Afrin,
Ma'am.
okay. Go ahead.
Good afternoon to one and all present here. I am Afreen, your co-host of this program. I'm honored to welcome you all today's webinar on the sun and the space weather, impact of our way of life. This is the 111th talk episode of the Reactive Online Weekend Talk. Reactive Introduction. Reactive is a group of the people who are like-minded and curious to gain new knowledge. Creative means creativity and active means active. Creative means to be active, we need to be creative. Knowledge square is our tagline. Sharing of knowledge increases our knowledge. The vision of Creative is to build the constructive thinking on various domains. Our main focus is on non-textual, non-academic, and non-syllabus concepts. Every Saturday, we organize online weekend talks on the Zoom platform, and we live stream our program on YouTube channel of Reactive JVD. Reactive is thankful for all our resource person for engaging with their knowledge. We encourage you to actively participate by asking the questions and engaging in the discussion at the end of this section. We are very privileged to have today's speaker, Dr. Janardhan Padmanabhan, sir, in Reactive. Our journey is to fascinating world of the solar activity and its effect on the earth promises to be both enlightened and essential in understanding the forces that influence our daily life. Let's embark on this illuminating journey into the sun's influence on our world and discover how we can safeguard our way of the life against the force of the space weather. Thank you for joining us all. Let's begin our exploration by introducing today's speaker, Professor Janardhana Padmanabhan. Obtained a PhD in 1991 from the Gujarat University. After his postdoctorate at ITFR, he joined the Physical Research Laboratory, PRL, Ahmedabad, as a faculty member in 1993. He was awarded as the elected fellow of the Indian National Science Academy, INSA, New Delhi. Currently working as an INSA senior scientist in the astronomy and astrophysics division of the PRL. He was formerly the dean at the PRL and the principal investigator around 2008 to 2020 of the Aditya Solar Wind Particle Experiment. A payload on board the ISRO observing the class of the Aditya L1 mission to study the sun and the energetic particle distribution in the solar wind. His research covered a wide range of interest from the radio studies of the sun and the solar wind, solar magnetic fields, and the space weather to commence exoplanets, experimental studies of the astrochemical ices and shocks processing of the molecule. He has been awarded with the Alexander von Humboldt at the Egerland Institute of the Radio Astronomy, Bonn, Germany, a recipient of the Vikram Sarabhai Research Award in the Space Science, ISRO Merit Award, Outstanding Contribution to its ISRO Space Program and Space Science. He was the research associate at the University of Maryland and has visited the professor position of the Institute of the Space and Environmental Science, Japan, and the National Institute for Space Science, Brazil. And also, he has also published over hundreds of pages in previous reviewed journals. I welcome you, sir. I welcome all the participants for today's section. I welcome Supriya ma'am and Srinath sir. for today's function. Over to Janan.
Well, thank you very much, Afreen. It is a great pleasure for me to have this opportunity to speak to you all. Before I start, I would like to thank the organizers, Supriya Madam, and also all of the audience who have taken time off from their personal schedules to attend this talk. So I'm grateful, and I would say it's a great opportunity for me to be able to interact with you young people. So let us begin. So basically today I'll be talking about the sun and space weather. We all know what is the sun, but not many may know what space weather is. So let's look for a moment at this picture here in the middle. It was basically a sticker that we made to advertise our instrument on board the Aditya mission called ASPEX, Aditya Solar Wind Particle Experiment, but that is not the focus of today's talk. What I want you to look at is what is represented here is the sun on the left and the earth and its magnetic field on the right. Okay. Now the space between the sun and the earth is not empty. It is filled with a material that is flowing out of the sun continuously, which we call the solar wind. And this solar wind contains plasma, it contains highly energetic particles, and it contains magnetic fields that have been pulled out of the sun into this region between the sun and the earth. Now this solar wind pervades the entire solar system. Even if you go to Pluto, you will experience the solar wind. So the solar wind between the sun and the earth, this region between the sun and the earth, we call the inner heliosphere. And as this material flows out at great velocities, at something like 450 kilometers per second. So eventually, all of this material in the solar wind will come and interact with the earth and its magnetosphere. And this interaction can change the conditions in the space around the earth. Okay. All of these changes that are caused due to events on the sun, which are transmitted by the solar wind to the earth, are referred to as space weather. Okay. And unfortunately, a large number of things that occur due to space weather are adverse. They affect the earth in an adverse way. And that is what I'm going to discuss today. Question is, how does it impact our way of life? Or does it at all? So this is a one slide summary of my entire talk. Okay, so let us move on. You now know that we have a solar wind. That solar wind travels at 450 kilometers per second from the sun, and it interacts with the Earth's magnetosphere and changes the conditions in near Earth space. Okay, so let us look at some parameters that we have basically of the sun and the Earth. The Earth is 150 million kilometers away from the sun. In terms of the amount of time that light would take to travel this distance, light takes only 8 minutes to travel 150 million kilometers. Okay, and we refer to this distance as 1 AU. 1 AU is the distance, is one astronom. A stands for astronomical and U stands for unit. So 1 AU is 1 astronomical unit representing this distance. Now, if you look at the mass and the volume of the sun, it's about 1 million times more than the Earth. Okay, and the radius, if you look at, the radius is about 108 times more than that of the Earth. And all of you know, speed of light is this humongous huge number, 300,000 kilometers per second. And the distance traveled by light in 1 year is nearly 10 trillion kilometers. Okay. Now, I don't know if you people have a feel for what is billion, million, trillion, etc. But if you were to count one number at a time, okay, continuously for 24 hours a day, you will take 30,000 years, 32,000 years to be correct, to count up to 1 trillion. That is if you took no rest at all. So that is the kind of distances we are talking about. And 1 light year is 10 trillion. So you take 320,000 years to count up to 1 trillion. So that's the kind of sizes that we have. Now, yeah, is there a question? No.
No, sir.
Okay. So now take a look at, now let us come to another topic. I've just told you the scales and sizes of the sun and the earth. Now, what is this picture that I have here? This little speck, which is pale blue in color, that is an actual photograph of the earth taken from a spacecraft called Voyager on Valentine's Day in 1990. Now, Voyager in 1990 left the solar system. That means it was slightly beyond Pluto, the last planet. Okay. Now, just before it bid goodbye to the solar system and carried on its way, it was made to take one last picture of the earth, and that is the photo that you have. That speck is the earth suspended in a beam of sunlight. Okay. Now, the famous astronomer Carl Sagan had this to say about that photo. That dot is us. That's home. On it, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives on a mote of dust suspended in a sunbeam. So I would like all of you, especially the younger generation, to reflect on this. That is the only home that we have. And we are destroying that home in so many myriad of ways. Okay. And apart from that, think about all the rivers of blood that have been spilled to control one small fraction of this dot. Now the Voyager spacecraft is 22 light hours away. At the time that it photographed this, made this picture, it was only 5 light hours away. So it's 4.5 times that distance now. If Voyager was to turn around and look towards the Earth and take a similar photograph, it will not even see the Earth now. So the entire Earth, all of us, although we have gigantic egos, we are basically a small little speck in this vast empty space. And we have to realize that we have only ourselves to depend on to save ourselves from our own follies. Okay, I'd like all of you young people to keep this in mind when you go out into the world. Now let's look at the radiation from the sun. Electromagnetic radiation from the sun is what I've shown here. The sun, 92% of all the emission from the sun comes either in visible or infrared, okay, and about 7% in ultraviolet. Now, what I have marked here at the bottom is the wavelength of this radiation in nanometers, and on top I have marked the energies of these wavelengths. So you can see at the violet end of the spectrum, the energy is 3 electron volts. Now, what is an electron volt? An electron volt is when you accelerate an electron through 1 volt of potential difference, a very small amount of energy. And you can see 1 electron volt is basically 1 trillionth of an erg. And we are all familiar with ergs and joules, I suppose. So what is the significance of this? 3 electron volts. Supposing you were to go out on to a beach in a sunny day and spend some time sunbathing. If you overdo it, you'll start getting boils on your skin because of sunburn. What is happening? What is happening is that the ultraviolet radiation from the sun, which is around 3 electron volt, is penetrating into your skin and breaking up the molecular bonds in your skin, and therefore creating boils on your skin. Okay, so at a mere 3 electron volts, that is happening. Now the sun's surface area is 10 to the 22 centimeters squared. If you divide that energy by the surface area, you will get the amount of energy per centimeter squared per second. So the sun radiates 10 to the 10 ergs per centimeter squared per second. And if you keep in mind 10 to the 7 ergs is 1 joule, you can see that it's a very small amount of energy. Now, to give you an example, if the stove in your kitchen produced heat at the same rate as the sun's surface was producing, then it will take you several years to boil 1 cup of coffee, because to raise the temperature of 1 cup of coffee from say 25 degrees to 100 degrees, you will need about 80,000 joules. Okay. So the point I'm trying to make is that life is a very low energy process. The digestion that takes place in our stomachs for the energy that we need to lead life happens at these energies, 3 electron volts. Okay. A simple mosquito flying at about 1.5 kilometers per hour will have about 1.5 electron volts of energy. Okay, so let me not overstress that point. I just want to tell you that life as we know it, carbon-based life, is a very low energy form of process. Let's quickly look at some history. The discovery of the sunspot cycle. See, 200 years ago, this fellow Heinrich Schwabe, who was a German, was a simple common man. He worked as a pharmacist. In those days, these pharmacists were called apothecaries. In our local language, you will call them compounders. But he had a funny idea in his mind. He thought that there was a planet that was orbiting the sun at a distance closer to the sun than the first planet, Mercury, and he wanted to discover it. So he thought it would be very easy to do, because all he had to do was to go and observe the sun every day. And if this planet was indeed orbiting the sun, then at some point it had to come in front of the sun, and you would see it as a nice, beautiful dot like this shown here. This is actually Venus moving in front of the sun, and we call it a transit. So this is the Venus transit in 2012. So for 17 years, from 1826 to 1843, this gentleman Schwabe went out every day when there were no clouds and observed the sun. And what did he see? What he saw was not a nice, beautiful dot like this, but he saw a lot of spots, which we call sunspots today. And being a good observer, he noted down the positions and numbers of these spots for 17 years. And he never found the planet that he was looking for. He, in fact, even had a name ready for it. He wanted to call it Vulcan, which is the name for the god of fire. And so after 17 years, he gave up, but he wrote down his observations in a book and then stopped observing the sun. Later, this gentleman, Rudolf Wolf, who was the director of an observatory, solar observatory in Switzerland at Bern, he read the book and he felt a little intrigued, because here was a common man coming and doing these wonderful observations, and he wanted to verify it. So he collected all the data on sunspots from the time of Galileo Galilei, and he analyzed it and found that indeed what Schwabe had said was correct, that the sunspot numbers actually increase and decrease with a period of 11 years. Okay. And although the period is fixed, the amplitudes, that is the number of sunspots in at any given cycle, those amplitudes can vary quite hugely. And when you had successive week cycles 3 times or more, then you call them, you give them a name. For example, this 5, 6, and 7 cycles are known as the Dalton minimum. Okay. So this red patch I have shown here is the patch when Schwabe was observing. So now we know, what do we know? We know now that the sun number of spots on the sun follows a cycle, or the sunspot cycle, represented here as SSN. And the sunspot cycle can go up and down with a periodicity of 11 years. Okay, I have shown here cycles 1 to 9. What Rudolf Wolf also did was he randomly labeled cycle that started in 1755 as solar cycle number 1. Because before 1755, there was not enough data to make a complete cycle. So cycle number 1 started in 1755, and we are currently in cycle number 25. Okay, the next big contribution to solar physics came by this gentleman, George Ellery Hale. He was an amazing scientist, and he discovered that sunspots that we see on the sun are actually regions of very strong magnetic fields. He used a spectrograph and the Zeeman effect to determine that these regions of the sun actually have magnetic fields about 1500 to 3000 Gauss. I've shown here a single sunspot. The diameter of this sunspot will be equal to the diameter of the Earth. And you can see the boiling that's taking place on the surface of the sun, which is at about 6000 Kelvin. So this was one of great contributions that Hale made. And later on, now we realize that magnetic fields are not just there on the sun, it's there everywhere in the universe. Almost everything in astronomy is guided by magnetic fields. If any of you visit California at any time in your life, do go and visit the Hale Solar Laboratory. It has been declared as a National Historic Landmark. Okay. Now let's look at some other aspects of the sun. See, the sun doesn't rotate like a solid body. Okay. Its equator spins much faster than its poles, just because it's a gaseous object. So this is called differential rotation. Okay, so the equator rotates once in 25 days and the pole rotates once in 35 days. The second thing we have to realize is, supposing this rectangle here represents the photosphere of the sun, which means the white disk that we see with the eye, it's called the photosphere. And if you have some magnetic flux underneath the photosphere, then that magnetic flux will tend to move up and pop out of the surface. Why is that? Because the internal pressure in this magnetic flux is generally less than the external pressure. And why does that happen? Because the external pressure is the sum of the internal pressure plus a contribution due to the magnetic field. Therefore, Pi will always be less than Pe. And therefore, magnetic flux will feel a force pushing it upwards. It's like trying to push a balloon under a bucket of water. Okay. So this magnetic field will eventually come out of the sun surface and go back into the surface. So magnetic field, the sunspots come in pairs. The foot points where they come out of the sun and go back into the sun, these foot points are called sunspots. So sunspots have a northern polarity and a southern polarity because they're magnetic, and you can see an actual picture here of these magnetic loops. Now what happens when these magnetic loops appear and the sun is rotating at different rates at different latitudes? These fields will get twisted. The fields will get twisted. And when opposite polarities meet, what happens? You have a reconnection like is shown here. And generally the reconnection of these opposite field lines takes place with an explosive release of energy. And if you look carefully here at this explosion happening on the sun, at the start, you can see a twisted flux rope. Okay, if you look carefully. So that's exactly what's happening here. When it reconnects, there is an explosive release of energy and matter is pushed out into space. We'll look at more of these kind of explosions at a later time. I had shown you earlier cycles, solar cycles number 1 to 9, and here is 10 to 24, and we are currently in solar cycle 25. You had another period, 12 cycles 12, 13, and 14, which we call the Gleisberg minimum, when the sunspot amplitudes were low for 3 successive cycles. Now, what is peculiar about, look at cycles 21, 22, 23, and 24. Okay, and what you'll notice is that they have been steadily decreasing in amplitude. Now, this has never happened before. From 1755 to now, we have never had 4 successive cycles decreasing in amplitude. And what is expected in solar cycle 25 from predictions and models is that solar cycle 25 will only be about slightly stronger than solar cycle 24. So we're actually in an unusual period of time. Okay. Now let's go to cycle 23. What do we see? Here I have plotted cycle 21, 22, 20, 21, 22, and 23. If you look at the minimum of cycle 23, it was a very extended minimum as compared to any of the other cycles. So we call that a deep minimum. Okay, it was the deepest minimum in the past 100 years, with over 250 days being entirely spotless in 2008 and 9, and over 150 days in 2007 being without any sunspots on the sun. Okay. And of course, because of this extended minimum, the cycle 24 started 2 years later. And what is additionally known about this minimum is that it experienced the slowest solar wind with the weakest solar wind dynamic pressure and magnetic field as compared to the earlier 3 cycles. Okay. Photospheric fields also declined by 52 Gauss per year from 1998 to 2005. So what we did is we went and verified, we wanted to know when exactly did this decline start. And here are the solar photospheric magnetic fields from the data that we analyzed. You don't have to worry about what is the process we used and things, but you can see there is a sharp decline in the solar photospheric magnetic field starting from about 1995. And then if you extend it, this dotted line is an extrapolation. If you assume that this decline will continue, when will it go to 0? It will go to 0 in 2034 if this thing continues. Now the lower panel is in the solar wind. Now again, you don't have to worry about what this normalized scintillation index and all that means. I'm just telling you that what this shows here is basically a decline in the densities in the solar wind. Okay. So the solar wind densities are also decreasing and with the same slope. And why does that happen? Because we call it solar wind microturbulence. And microturbulence is seeded by solar magnetic fields that are pulled out into the solar wind. And so they have to decline with the same rate. And we verified that. So solar wind microturbulence and photospheric magnetic fields both are declining, and if this decline continues by 2034, question is, will sunspots disappear? Okay. Now, when density is reduced, what happens? The force with which the solar wind hits the Earth's magnetosphere reduces. Okay. It's called the solar wind dynamic pressure. So the solar wind dynamic pressure will reduce. If the solar wind dynamic pressure reduces, then this RMP, which is the magnetopause standoff distance, this is the Earth. Okay, this is the magnetopause and this is the bow shock. This distance will move outwards, as will this distance move outwards. Okay, because this dynamic pressure, which is hitting the sunward side of the Earth's magnetosphere, will reduce. This red circle is the geostationary orbit. This is where we park all of our satellites, which we use to connect to our TVs and all that. If you looked at the TV antennas on your terrace, you'll see that they're all pointing at one point in the sky. The antennas are not moving, but the satellite is moving. So how come you're able to receive the satellite? That's because at this geostationary orbit distance of 6.6 Earth radii, one rotation, one revolution of the satellite is 24 hours. So the speed at which the satellite moves with respect to the Earth is the same. So it appears not to move. It is like two people walking side by side. Though they are both walking, they are both next to each other all the time. Okay, so that's an important orbit for having any kind of communication. Now, has the solar wind dynamic pressure reduced? Look at the panel here on the right. I have plotted the solar wind dynamic pressure. We needn't bother about how we got this and the technical details and all that. The red points are that solar wind dynamic pressure, PD, from the 1995 to December 2007. And the black points are from 1975 to 1994. And clearly you can see that there is a decrease in the red points are all lower than the black points. So there is a decrease in the dynamic pressure. And then you expect, if you look at this lower panel here, these are the number of events where the bow shock, previously I told you the bow shock sits at around 14 Earth radii. So all the events that when the bow shock came greater than 13 Earth radii is what is plotted here. And you can clearly see that the total number of events since 1995, where the bow shock moved outwards, is much greater than prior to that. And what is here on the top left panel is a model that we created. We modeled the shape of the magnetosphere, okay, using actual data. And you can see that this red line corresponds to 1996. This is where the magnetosphere was in terms of solar radii. And in 2020, it was represented by this blue line, okay? And in 2008, at the deepest solar minimum, it actually went huge from 9.5, 9.6 to 11. So the magnetosphere has on average expanded outwards by about 1 Earth radii since 1996. Now the question I asked earlier was, can sunspots actually disappear? So if you look in the past, we have one period of time from 1645 to 1715 when there were no sunspots or hardly any sunspots. And such events are known as grand minima. Yeah, is there a question? Hello? Is somebody asking a question? Hello? Hello, who is talking in the background? Hello? Is somebody talking in the background?
Sir,
Okay,
you can
so-
continue.
Yeah. No, I was thinking somebody was asking a question. Okay. So these are grand minima when you don't have sunspots for say 50, 60, 70 years. Okay. And what happened during the last grand minima was that there was a cooling of the Earth. Shown on the upper panel is that the blue represents cooling, the red represents heating. So globally there was a cooling. And in fact, in Europe, in England, for example, the Thames River, the famous Thames River froze, became completely solid, which has never happened after that. And even in Amsterdam and other places where there are a lot of canals, everything froze. And so it became so amazing that people actually made paintings of it. Here's a painting of frozen Thames. Okay. So question is, I've shown you that our sunspot magnetic fields are declining, and maybe it might go to 0, which means we might get another grand minimum like period. So question is, will that lead to cooling, global cooling? Right. Now, let us look at some other things. See, generally, when you want to look at the atmosphere of the sun, which we call the corona, you do it, you can see it only when there is a total solar eclipse. At the bottom, the small panel is a total solar eclipse of 1980, which was visible from India. And I would suggest that if any of you have not seen a solar eclipse, please make an opportunity to go and see one. It is worth it. It's something really spectacular. So this eclipse is this is a picture of the eclipse, and you can see this black disk is actually the moon coming in front of the sun, blocking out the brightness of the sun, and therefore you can see the atmosphere of the sun, the corona, which is about 1,000,000 times fainter than the disk of the sun. But today we can actually create an artificial eclipse from space. So this is actually this blue disk here is a disk which is covering the sun, which is represented by the white circle. So that white circle is the sun behind this disk. So this is done by a spacecraft called SOHO, which is in space. And when it blocks the sun, you can see the corona. And what is happening here? This is solar maximum. Look at the way there are explosions taking place on the sun. And this is solar minimum. So you can see there's a complete difference between what happens in solar minimum, what happens in solar maximum, and that is a comet actually passing behind the sun. So you see there is matter being thrown out of the sun at huge velocities. How much matter is being thrown out? 10 to the power of 13 kg of matter in each ejection. I mean, try to imagine that number, that is 10 billion tons of matter in a single ejection, and it travels at roughly 2,000 to 3,000 kilometers per second towards the Earth. Now, if you had 1 CME, there are much more than 1 CMEs here per day. Even if you took 1 CME per day, this is equal to 10 to the 8 kg per second. And the total amount of mass lost by the solar wind from the sun is only 2 into 10 to the 9 kg per second. So at solar maximum, these explosions, which we call coronal mass ejections, are actually responsible for 5% of the total mass lost by the sun. Okay. So that's solar maximum and that is solar minimum. Question is, what happens when these things come and hit the Earth? Because I'm talking about 10 billion tons of matter that come and slam into the Earth's magnetosphere. Okay. Now, if you imagine a straight line going from the Earth to from the center of the Earth to the center of the sun, then any material traveling along that line will come and directly hit the Earth. If material is traveling at an angle to that line, as is happening here, then this material will actually miss the Earth. So if anything happens right at the center of the sun, then it will travel along the line joining the sun and the Earth, and it will actually hit the Earth's magnetosphere directly. Okay. So now just look at this. There is a CME. If this kind of what we call a halo CME has actually occurred exactly at the center of the sun. How do we know that? Because the CME will start expanding radially outwards, and after some time it will be visible all around the sun like a halo. So these halo CMEs are the dangerous ones. Now, what happens when the halo CME comes and hits the Earth? Here I've represented it here. It will come, hit this and compress this magnetosphere. Okay, as you can see here. And in addition, if the material that comes out of the sun drags with it in the solar magnetic field, which has a southward component, then this southward component of the interplanetary magnetic field can reconnect with the Earth's magnetic field. The Earth is actually like, you can imagine it as if it has a magnet inside, which has its north pole in the southern hemisphere and south pole in the northern hemisphere. That is why compass north points to the north, because it is attracted by the south of the Earth's magnet. So if these two are oppositely directed, then you can have a reconnection that happens here. And then all those energetic particles, which are in millions of MeVs or hundreds of kilo MeVs, they can enter the Earth. Now I told you 3 EV can damage us. So if you have kilo electron volts and mega electron volts and things, it will actually do a great deal of damage. Luckily, we have a magnetic field that keeps all of that out. Now, how do you know that this kind of an event has happened? When this kind of an event happens, the Earth's magnetic field gets perturbed, And therefore, you can measure that with a magnetic station. And this is the kind of signature you get from such a disturbance. So the magnetic fields, the Earth's horizontal component of magnetic field first increases, then it decreases, and then it slowly comes back to normal. Now here is what we call an intense storm. And the reduction is about 250 nanotesla of the Earth's magnetic field during that event. We call it intense. Now take a look at this movie, which depicts how that storm happens. Let me just move it forward a bit. Okay, so this is what happens, that the CME comes and hits. There is a reconnection that happens here and breaks the field lines. These field lines are swept backwards. Okay, and all these particles get loaded on these field lines, and there is another reconnection that happens on the tailward side. And when that reconnection happens, these energetic particles enter the Earth's atmosphere and create the aurora. All of you are aware of what the aurora is, right? These are particles, energetic particles interacting with the Earth's atmosphere, causing colors. By interacting with nitrogen and oxygen, it creates a lot of beautiful colors. Now, I'm going to talk about an event that occurred in 1859. On 1st of September 1859, there was a person, Lord Carrington. He observed, he was looking at a projected image of the sun when he saw an explosion on the sun in white light, which is very unusual. It has to be extremely bright for that to happen. So this is called a white light flares. And 18 hours later, a major geomagnetic storm occurred. Okay, so it was obvious that a disturbance coming from the sun to the earth had caused this aurora. And I'm showing you just here a couple of pictures of the aurora. If any of you travel to the northern hemisphere, to places like Canada and Sweden and all that, you can actually look at, watch these aurora in the night sky. The beautiful colors dancing in the sky. Now take a look at this 1859 geomagnetic storm. I told you minus 250 nanotesla was huge. This thing went to minus 1,600 nanotesla. Okay. And if you look at all of the really biggest geomagnetic storms that we have had, nothing exceeded 600 nanotesla. So this is almost 3 times bigger than anything that we have had. So the Carrington CME was the most intense geomagnetic storm in recorded history. And it was, the aurora caused by this geomagnetic storm was so bright that you could read by the light of the aurora. Okay. And in fact, miners who are working in the Rocky Mountains, they actually woke up early thinking it was already daylight and started cooking breakfast when it was not daylight yet. So this was the strength of this one event. Okay. And also the telegraph, that was the only piece of technology that existed in the West in those days, which was the telegraph. And the telegraph, even after the operators disconnected, the batteries continued to work for the whole day, because the impact of this event created ground currents which were taken up by the earthing systems and actually flowed in the cables. Now we have had all of this data which I've shown you here on the left is actually taken from an observatory, a magnetic observatory that we have in Colaba. Okay. And that has been operating from 1845 and to this day it is operating. Okay. Now what happens when the CME comes and hits the earth? Now I've told you that it will compress the bow shock and the magnetopause. Okay. So how much will it compress it? Can it compress it and expose the satellites in this ring, geostationary orbit? Okay. Take a look here. I've shown you a table of, you know that this geostationary orbit is at 6.6 Earth radii. Now we have looked at all of our data and pulled out times when the magnetopause actually went almost to 6.6 Earth radii. And you can see, if you ignore the ones that were not there in the, 1968 and all that was, we were not so dependent on technology. But today, We're completely dependent on the satellites that are orbiting the Earth. Okay. And in fact, for the younger generation, without Facebook and without WhatsApp and all that, they will probably get depression in 10 minutes if they don't have it. So look at 1991 and 2005. It went to 6.83, 6.51, 6.99 Earth radii for 10 hours, for 9 hours. That means this orbit was exposed to high energy particles for 10 hours on those two occasions. And a single CME, when it comes and hits the Earth, you see this dots that you see are actually those high energy particles hitting the detector. And you have as many as 10 to the power of 11 particles per second per meter squared at the detector at 1 AU. Okay. So if an 1859 type CME happens today, it will be catastrophic. Why is that? Because shown here on the upper panel, every dot is a satellite. And this ring out here is the geostationary orbit. You can see how heavily occupied by satellites it is. And I have blown up the central part. Behind this white screen is actually the Earth, and each dot here is a low Earth orbit satellite. So if such a CME actually hit the Earth, like the Carrington event, then it is possible that a large number of satellites orbiting the geostationary orbit and including many low Earth orbit satellites will actually be destroyed. So I've already shown you this. So now let us look at what are the other effects that happen. Okay. Now, if you take the ionosphere, what is the ionosphere actually? It's a lot of charged particles moving around, and therefore there are millions of amps of current in the upper atmosphere of the Earth. And when the Earth's magnetic field fluctuates because of these impacts, you can create ground currents, ground-induced currents, which can enter our power systems and travel to the generating stations and actually burn up the transformers. I've shown here a plot. Our transformers, large power transformers, are actually immersed. The soft iron core is immersed in an oil bath. Okay, and here's the temperature of that oil during a geomagnetic storm when there are ground-induced currents. Okay, and you can see in a matter of few minutes, this is 409 and this is 539. Okay, this time is in minutes. In a matter of minutes, the temperature goes up from 50 degrees to nearly 200 degrees. And so that is really dangerous, really dangerous. Here is the damage. For example, in 1989, there was a huge power outage in Quebec in northern Canada. And that's because their power transformer got blown out by a CME hit. And that's the damage to the transformers. So if one of these large power generating transformers get burnt up, then what happens? Then you lose power. And if one transformer loses power, for safety's sake, all the other transformers in the grid will also trip. So the entire state or the entire country can go dark. Okay. And then you don't have any spare transformers to restart it. And when you eventually get a spare transformer and restart it, you will have what is called a cold load pickup. That means all loads are switched on and drawing current at the same time. And you have seen, even after a small, loss of power for a few hours or few minutes, and the power comes back again. In the old days, all our filament bulbs used to burn out, used to fuse. So that's what will happen. So not only will you not have power, hospitals, ambulance, emergency services, all this will be affected really badly. And when power comes back up again, all your equipment will get burnt out. Radiation exposure. When you have satellites in space, I've shown you, the spacecraft can actually get charged because all these energetic particles, electrons and protons hitting it, the spacecraft surface is a floating point. The surface will get charged to very high voltages. Okay, and it can actually start sparking between different components. So that will destroy the spacecraft. There will be increased spacecraft drag. And there'll be radiation damage, what I showed you of all those energetic particles hitting the detector. The detector will get degraded. And if you happen to be an astronaut in space at the time of this happens, then the amount of radiation exposure that you get will go up enormously. So radiation exposure, essentially we measure the dosage of radiation that we get in this unit called sieverts. And 4 to 5 sieverts can kill you. And 1 sievert is what? 1 joule per kg. Just like to remind you, what is 1 joule? If you took the resistor of 1 ohm, okay, and passed 1 amp of current through it for 1 second, then the heat dissipated by that resistor is 1 joule. Okay, so pilots, they experience about 6 millisieverts per year. The common man, depending on where you live, can experience between 3 and 5 millisieverts per year. If you live on the beaches of Kerala, where there's a lot of thorium, then you'll probably get as much exposure as the pilots do. And astronauts can experience 100 to 200 times more, provided if they're in space. Because when they go into space, they're always inside some capsule, so they don't directly get that. And just to know, in comparison, a single chest X-ray is about 0.1 millisievert, and a dental X-ray is about 0.005 millisievert. Other things that can happen is that these fast-moving, high-energy particles can actually get into your transistors and produce wrong signals. So the spacecraft will suddenly start misbehaving. These are called single event upsets. Okay, so suddenly the spacecraft starts behaving in a funny manner, you know that some such thing has happened. Okay, oil and gas pipelines. You have oil and gas flowing under the sea through pipelines, supplying various countries and all that. Now, when this geomagnetic storm happens, here's the quiet time and geomagnetic strong time. You have actually meters inside these pipes to measure the flow of oil or gas. Okay, if these currents enter in there, they can actually give you wrong signals. And the person on the surface will think, oh, the pressure has dropped, I better increase the pressure. And if that happens, the pipe will burst. Also, the sea acts like a large battery. Okay, and the pipeline will act like an anode. So material will start flowing away from the pipeline into the sea. So this pipeline will corrode at a very rapid rate. So all undersea pipelines are maintained at a negative potential so that it doesn't act like an anode, or rather it acts like a cathode. Now, when a ship goes into sea, same problem. The material of the ship will actually flow out of the sea like an electrolytic reaction. So they actually have what are called sacrificial anodes. Okay, these white things are sacrificial anodes. These are metals which have a electrochemical potential which is greater than that of the steel, and therefore material will preferentially flow out of these sacrificial anodes. I've shown one here. See how the material has gone out of that anode rather than from the ship preferentially. So oil and gas pipelines can be affected. Navigation can be affected because suddenly the density will increase in some path to the satellite. Okay, and this is called scintillation. And so the GPS satellites will not be able to get a position at some time. Now, have these kind of extreme events happened in the past? Yes, a number of them have happened, really extreme events. The biggest one happened 7,176 years before Christ, okay, BCE, which is about 9,000 years from the present. Okay, how do you know that? When these energetic particles come and interact with the elements, with the atoms and molecules in the Earth's atmosphere, they can create beryllium-10. Beryllium-10 is radioactive. Okay, and in the northern regions of the Earth, it settles on the ice and gets buried because continuously the ice layers are building up. So when you have strong solar activity, you have or when you have weak solar magnetic fields, okay, you have more of these charged particles coming because strong magnetic fields will deflect charged particles. So when the sun's field weakens, like I've showed you now it is, then you will have more creation of beryllium-10. Okay. So you, by looking at the beryllium-10, you can figure out that there was a weakening of the sun's field or a strengthening, or in principle, you can work out the solar cycle. So here is this event of 7176 BCE. There's a huge increase in the beryllium-10. Okay. And that is expected that it was 2 orders, about 100 times more strong than the Carrington event. And 3 other events that have been detected in beryllium-10 data are listed here. Okay. And this one, 774 in May, this 5-4 is April, May, etc. This was 10 times more than the 1859 event. So any similar magnitude event in the present would be catastrophic for life as we know it today. Okay. So what do we have to do? We have to save mankind. We have to use technology. We have to change the ways that we behave. Now, 65 million years ago, a huge asteroid came and hit the Earth here at the Yucatan Peninsula and destroyed the dinosaurs and wiped out large number of life on the Earth. Okay, life forms. 164 years ago, we had the Carrington event, but luckily at that time we did not have technology in space. And today, what are we doing? We're trying to meet the demands of mankind, whose population is going up and up and up and up. And this is what is happening to our forests. They're all disappearing because mankind needs to fulfill his greed, needs to have furniture, needs to have all kinds of things. So I'm just showing you a picture of a representation of the Aditya spacecraft here before I end. What is this tower here? 2 things sitting, THA1, THA2, and this STEPS 1 package here is our experiment, which we call Aspects, and that was built by the PRL team, and that's going to this point called L1. But I won't talk about that now. I would like to end here. I'm sorry for taking a little more time than planned. So if you have questions now, I'd be very happy to answer any of them. Thank you.
If you have questions, you can raise hands so that I can unmute you. Participants. Yeah, you can unmute yourself all and you can ask.
Hello. Hello, may I ask a question? Hello,
Sir,
can I ask a question?
yeah.
Hello, thank you very much for a very nice talk, very informative talk. I want to know, you talked about sunspot minima occurring during certain periods.
Yes.
Does it happen periodically? Can we predict this happening of sunspot minima? Is there any way of predicting the occurrence of sunspot minima? Or if not, why do they happen so randomly? Because the solar motion, we expect that to be very periodic. Why this kind of minima?
Okay, there are 2 types of minima here. One is the solar cycle minima that happens every 11 years.
Yes.
Okay, that is a periodic event. It happens every year. It can be predicted, modeled, and so on and so forth. The other thing is this grand minima, which I spoke about, where for 50, 60, 70 years, there are no sunspots. Now, the only way that people can study this is by using this beryllium-10 and carbon-12 radioactive data, because carbon-12 and beryllium-10 are formed by this cosmic ray interaction with the molecules in the Earth's atmosphere. And that happens, like I said, when the magnetic field of the sun is weak, you get more cosmic rays. And so you get more beryllium-10.
Yeah.
And so people have looked at this carbon-12 data from tree rings for the past 11,000, 12,000 years they have looked at. And they have found 27 grand minima in that 11,400 years of data. So it is not that these grand minima don't occur. 27 of them have occurred in the past 11,000 years. Okay.
Yes.
So then they have taken that data and tried to model it to see what are the conditions that can drive the sun into a Maunder minimum.
Yes.
And they have come up with a number of conditions. For example, the period of the cycle will increase before this happens. And I've shown you cycle 23, the period already increased by 2 years because we had a very deep minimum in that 2 years. Okay. And then there are other things that I have shown, that the meridional circulation, these are technical details I can't get to, but yes, there are certain conditions that need to be met for these things to happen. But still, this is based only on 27 events. And this beryllium-10 data is not like directly observing the sun. There are large errors in these things. But I think if this trend that I've showed you of the solar magnetic field is reducing, and it is still reducing to this day, it has reduced by over 40% now. Maybe by the end of the next cycle, we will be heading into a Maunder-like minimum, and maybe we'll be getting a lot of cooling, global cooling.
What is the explanation for the 11-year cycle, sir? What is it? Can you explain? What is it based on? Is it based on the movement of the planets and all that? Why do you get this 11-year cycle?
No. It has nothing to do with the movement of the planets. The 11-year solar cycle is controlled by what is called a solar dynamo. Okay. Inside the sun, there is this movement of magnetic field. Magnetic fields are first of all generated deep inside the sun by currents. Okay. And it follows a certain dynamo, both in the northern hemisphere and in the southern hemisphere. And we can completely reproduce the cycles from cycle number 1 to 25, except in this small period when 23, 24 and all that were peculiar. They were not following exactly the models because solar photospheric fields are weakening. And there are several predictions, including we have predicted for the amplitudes of solar cycle 25 and 24. And the predictions are all falling in that ballpark, but we have to see what actually the sun does. If it does what we expect, then we think we understand the sun, otherwise no. So there is no involvement of any planets or anything. It is simple physics that is occurring at in what is called the tachocline in the sun, which modulates which creates the solar dynamo, the magnetic fields, and the sunspots.
Okay. Well, one last question, sir.
Yes.
You mentioned about initially the path of Voyager leaving the solar system and going away. Where is it going, and how is it being powered? Does it go on for how long? Does it go on in space?
It has a nuclear powered system.
Where is it going?
It has left the solar system now, and in the next 50,000 years, it will reach the closest star system, Proxima Centauri.
Is it sending any signals? Is it sending any signals?
It is still sending signals. Can you believe that? It was launched in 1977. And we are still able to track it. And can you believe that it has only a small dish antenna of a few meters in size? That antenna has to be pointed exactly at the Earth.
Yes.
Otherwise, the signal will miss the Earth by hundreds and thousands of kilometers.
Yes, I understand.
Still doing it to this day. It is 22 light hours away.
Yes, that's very
Pluto is
amazing.
only 5 light hours. And Voyager 2 is doing the same thing. Voyager 1 and 2 are both launched in the 1977. Voyager 2 is a little behind. Voyager 2 is about 18 light hours away. And this one is 22 light hours away, but both have left the solar system. And hopefully they will reach the closest star system when they reach the closest star system about 60,000 years from now, they will still be humans on this earth, provided we don't destroy everything that we have. Yeah.
Thank you.
Yeah. This, by the way, is our observatory in Mount Abu,
Uh-huh. Yes.
ERL's observatory. Yeah. Any other questions?
Yeah, may I ask a question?
Please, please.
Yes, thank you, sir, for your informative talk as well. My question here was that we have had this. Sir also asked this, but just adding on to it, we have this periodic way of our minimas every 11 years or so. Then there's a grand minima, etc. My question was that during this period, if this another grand minima were to happen in X years or Y years, whatever, then how would it affect our satellites and communication? Of course, we would have a mini ice age. Many of our rivers can flood, including the oceans. But how would that affect satellite and communications that we are currently able to do?
Yeah, the satellite systems per se will not be affected. Satellite systems will be affected only by these CMEs. But when you have low magnetic fields on the sun, then I told you the solar wind dynamic pressure weakens. And when that weakens, our Earth's magnetic field expands outwards, like opening an umbrella. You see, it expands outwards. And therefore, Earth's magnetic field also becomes weaker. And at this time, more cosmic rays can come into the Earth. Cosmic rays are very high energy particles.
So it's more vulnerable to another
Yeah.
sea.
So more of this high energy particles can come in, more it can destroy the ozone layer, can cause more cancer, these kind of things.
Right. And secondly, in one of your images, we have seen that the sun, since it has a high amount of radiation and a high amount of light, so to block it out, to focus on the atmosphere, we try to block it out like with that disc-shaped object, SOHO, that we have placed in the sun, in an orbit around the sun, of course. So my question was that around this orbit, these type of spacecraft, since such type of technology, SOHO has been launched in from what I believe 1985. So what type of instruments can be used to create a similar simulation in order to focus on one specific area of the sun?
Yeah, actually, I couldn't quite get your question, Venkat. You're asking what kind of instruments we are using on these satellites?
Yes, to create an artificial solar eclipse.
Okay, so in principle, it's very simple. You have a disk. It's like supposing you take a 1 rupee coin and you hold it in your hand until it blocks out the sun.
Yeah.
You can do that very easily.
Yeah.
Okay, it's dangerous. Don't do it because you'll be looking directly towards the sun. But in principle, a small object, a small disk held at a correct distance can block out the sun.
Yes.
Right. So that's the principle on which it carries a disk. So you have two types. You have two types of this instrument is called a coronagraph. The two types of coronagraph. One is what I showed you. Like you actually have a physical disk and you block the sun. Okay. The other type is called an internally occulted coronagraph, where you image the sun and you send that reflected image to another mirror where there is a hole in that mirror where the image of the sun will go out into space. And only the corona will be imaged.
Okay.
Are you understanding? You form an image of the sun.
Yes.
Now you put that image of a sun on another mirror. And that mirror has a hole exactly equal to the diameter of that image of the sun.
Okay.
So the light of that image will go through the hole and go away into
Yes.
space. But the rest of the stuff, the corona, will reflect from that second mirror and form another image somewhere, which is the
Like-
corona, which you can see. So that's an internally occulted coronagraph. And what I showed you is an externally occulted. Now for this stuff to happen properly and to get very sharp images, these mirrors and all that have to be polished to some extraordinarily high degree.
Mhm.
Okay, and we have a coronagraph now on Aditya,
Mhm.
okay, which will do the same thing, except it will go a lot closer to the sun than SOHO.
Okay. So does that mean that instead of placing this on satellites, can it
Can you
also
speak a little louder, please?
instead of placing it on satellites, can it also be placed on ground systems?
Actually, because of the atmosphere of the Earth and the diffraction that is caused, we can never get clear images of the corona. The corona is 1,000,000 times fainter than the solar disk. You need to go to space.
Okay, got it.
Hmm.
Yes, sir.
Any more questions? Yeah, it's time to end up the program. Sir, thanks a lot for your time and the knowledge sharing. And I thank all the participants also. It was great pleasure to be here. I can end up the program. Yes, sir.
Yeah, so thank you all. Thank you, Supriya, and thank you everybody for taking time to listen to this. I really appreciate that.
Thank you, sir. Thank you very much, sir.
Thank-
Afrin, we can end the program.
Yes, sir.